Hello everyone, this is the lecture for Applied Statistical Analysis, Week 6. Today we're going to be talking about ANOVA, both one-way and two-way. ANOVA can do a lot of things, and there's a lot of different types. We're going to start with the two most basic versions, and then maybe we'll be able to talk about a few other things with it later on. We've learned several different tests at this point, so I made this diagram to try to help us keep it straight where to go. So we're going to walk through each part, and then at the bottom all the orange is ANOVA, and we're going to talk about those. So the first thing we learned about was z-tests, and the question is, do you know comparison population mean and standard deviation? If yes, then do a z-test. If no, which is very common, then do we know the comparison population mean? And if so, then we just do a regular t-test, a single sample t-test. If not, then how many groups or repeated measures do you have? If we only have two groups or two repeated measures, like a pre-test and a post-test, then we come right back to the t-tests. And when we do, the question is it repeated measures or not? And if it is, then we do the paired samples t-test. If not, we do the independent samples t-test. Over here, if we have three or more groups or three or more repeated measures, like a pre-test, mid, and post-test, then we're going to consider ANOVA. With ANOVA, the question is, again, do we have repeated measures? And if so, then we're using repeated measures ANOVA. Good name, right? If not, then we have to ask the question, do you have two independent variables? Or in other words, two different grouping variables, like one of them could be the treatment and control. That would be one group. And then another one could be gender or race, or do they play the piano? So if we have more than two variables, even if they only have two levels, we're still going to go the ANOVA path. I know it's not super clear in this. This is not the most thorough graphic, but hopefully it helps you kind of go in the right direction. So if we do have more than two variables, or we have two or more, then we're going to do the two-way ANOVA. If we don't, then the question is, do we have other things we want to control for, called covariates? We're going to talk about that later on. So you don't have to worry about that too much, but if you do, we're going to do what's called ANOVA. And if not, if we just have one variable and it's a grouping variable, we're doing one-way ANOVA. ANOVA stands for Analysis of Variance. And it's a whole class of methods like we showed. There's several that we can do, and they're generally used with experimental designs. They're best if used with experimental designs. It has very similar assumptions to the t-test and gives us what's called an omnibus result. It means it has just given us an overall result. So if we have three groups, it's not going to immediately tell us which group is different from the others, or if they're all different. It's just going to tell us if any are different. So we just get one result. The table down here shows us what an ANOVA table usually looks like. So usually we'll have the variable name, and it's going to have a number of numbers. So the sum of squares, your degrees of freedom, the mean square, the f, and the p. As we've done before, the p-value is the exact same thing, but now we're going to be using the f statistic instead of the t statistic to get it. And the f statistic looks like this. So instead of being a nice normal curve, it doesn't go below 0, and it has this peak, and then it just has this long tail. It just goes out here. And so just like with the t-test, we're going to say, based on where our result is, we're going to draw the line and say what's the probability of getting a result that extreme or more extreme given that the null is true. So let's come back to this. There are several types. Today we're just going to be talking about the one-way and two-way ANOVA. One-way just means you have one grouping variable. Two-way means you have two grouping variables. General requirements. First, you need a dependent variable that is continuous, so it's on an interval or ratio scale. And you need an independent variable that defines two or more different groups or time points. So an example would be this. Our outcome is this continuous variable. And then we have a group that says whether person number 1 is in group 1. Or if you go down, person number 5 is in group 2. It also can handle data that looks like this, so time 1 and time 2. One thing that you need to be aware of is ANOVA can handle just 2 groups, but your results end up being exactly the same as a t-test. So generally when you just have 2 groups, 2 levels in your group, then you just do a t-test, but an ANOVA can handle that. So we're going to go through an example. Hopefully it helps some things make some sense. We're going to do the same exact 6-step approach. So step 1 is looking at the assumptions. These look very similar to the t-test. So independence of data, the individuals are independent of each other. So one person's scores do not affect another's. You need the appropriate measurement, which you need the interval ratio dependent variable. The normality of distributions. This one is slightly different than the t-test, but still very related. You need normality of the residuals. We'll talk about what that means. It's basically the stuff, the noise, everything left over. But overall, if your outcome is roughly normal, the residuals will be too. And this is often how we look at it. We're going to use what's called a QQ plot. And we just want these dots to roughly go along this line. And so this situation right here that I show, it's not bad. The dots, for the most part, just follow the line all the way up. The last one, homogeneity of variance. So this one is the variances of the groups should be equal. So this assumption is not super strict if the groups each have similar sample sizes. So if we have 5 individuals in each group, then we might be fine. But again, this is just, we want the groups to have similar variance. So similar amount of movement in each group. So we talked about examining them. We want a random sample. We've got to know what our variables are. Normality, we're going to use the QQ plot that I showed. And then homogeneity, again, Levine's test. With Levine's test, we're just going to always rely on Jamovi telling us what the results are, and we can interpret from the Jamovi output. Step 2 is stating the null and research hypotheses. And this one is interesting. So with the ANOVA, the null hypothesis is that all the means are the same. So each group has the same mean. Verbally, that means there is no real difference between the groups. So the differences in our sample is just sampling error. For the research hypothesis, it says at least one mean is different than the others. It's not saying that they're all different from each other. It's just saying if we reject the null, we're saying at least one is different from the others. Maybe all of them are, but that's not necessarily what our claim is. So verbally, one of the group's means is different than the others. The difference would be created by something that's real. There really is a difference between the groups. So I'm going to go through this one really quickly again. It's very much the same as what we've done. For ANOVA, we're again just going to define an alpha level, say 0.05. So you decide an alpha level before you collect your data, and then you can calculate the critical value. You would use a table like this. We're not going to go over that because we're going to use Jamovi for it. The one important thing is that you now have 2 different degrees of freedom. you have the degrees of freedom numerator, and that is g minus 1, where g is the number of groups. So if we have 3 groups, then we do 3 minus 1, so our degrees of freedom numerator is 2. And then we have a degrees of freedom denominator, and that is n minus g. So your total sample size minus a number of groups. So if we have 15 people and 3 groups, then our DF denominator is 12. So we'll see this in the table when we see the example. So again, for this step, we would just state that we're defining our rejection region as alpha less than 0.05. So if our alpha is equal to 0.05, we're just saying anything, a p-value below that, we're going to reject the null. All right, and then we compute the test statistic. In this case, it's going to be the F statistic. We're going to let Jamobi do this. You can see there's a lot to this, but we're going to walk through each part so you at least understand where things are coming from. You don't need to memorize the formulas, but it is good to know where they're coming from. So the first thing is the sums of squares. We're just adding up all the squared deviations, essentially like a standard deviation. So this is a sort of measure of a standard deviation. The reason why we call it ANOVA is we're trying to understand different pieces of variance. So we call it an analysis of variance. We're trying to understand different pieces of it. So we have the between groups variance, that's what this is trying to get at. And then we have the within groups variance, which is what this is trying to get at, and then you have the total variance. To help illustrate that, so let's say this is our data. We are looking at some outcome, and that's Parks and Rec in the office. So all the variability within the group, so say Parks and Rec, is all of this. So the people in Parks and Rec vary from up here to down here. They vary quite a bit. And so this would be part of our measure of the within group variation, the residual. This is all the stuff we can't really explain. We don't know why there's so much variability within the groups. And so when we're thinking about within group variation, it's just all the noise within the group. So this is some of it right here. And then for the office, this is how much variance we have. Together, they make that full within group variation. That's all the variability within the groups themselves. We're going to compare that to how much it varies between the means of the two groups, basically. In this case, we're saying this group is up here, this group is down here, so this is the amount of variation between the groups. Within group variation, all the variation within the group. Between groups variation. That gets translated into what's called the mean squared and then the F statistic. All of these are ratios. So we have the sums of squares between that we got here, and the degrees of freedom between, which we get here, and the sums of squares residual and the degrees of freedom residual. The DF is the numerator here, oops, and the DF is the denominator here. These then feed into the F statistic. What these are trying to answer is this question right here. Is the amount of difference in the means big compared to how much variability there is in the groups? In other words, is this difference big between these groups compared to how much variability there is within the groups? I'll give more examples of this in class. So if you do have questions, make note of them, put it on the discussion so that we can talk about it. The F statistic and the p-value tell you if one of the groups is different than the others. In other words, is there some differences between the means of the groups that's really big compared to how much variability there is within a group? The issue is it doesn't tell you which ones are different. If we have, let's say, 3 groups, all we know is that at least one is different from the others. But usually when we use ANOVA, we want to be able to say which of the groups is actually different. Are they all different from each other, or is one of them different from another? To do that, we're going to do what's called post hoc tests. It also can be called contrasts. Post hoc usually refers to comparing all groups with each other and making an adjustment for the multiple comparisons. We're going to talk about what that means in a minute. Whereas contrast usually refers to comparing some of the groups with each other based on predetermined questions. In other words, we use the ANOVA to see if there's any differences, and if we find a difference, if the F statistic is significant, then we dive in and see where are those differences. We could just wonder, is group 1 and 2, are they different from group 0? And if so, that would be called a contrast. And these are basically just t-statistics at this point, where we just say, is group 1 different from group 0? Just like we've done in the t-test. We're just comparing those two. And in this case, it's not. And then we might be also interested in comparing group 2 to group 0. And in this case, that is also not significant. When we're doing just regular post hoc comparisons, usually we're comparing all of them. So 0 to 1, 0 to 2, and 1 to 2. And often what we do when we do those is we make an adjustment for our p-values. We'll talk about why later on in the class, but the idea is that every time we make a comparison and we're basing it on a probability, there's a chance that we are making the wrong decision. By making an adjustment, that reduces that chance that we are wrong. When we do many comparisons, in this case just 3, but sometimes we have many more. What I point out here is that these two comparisons are the same. It's comparing group 1 with group 0. In this case, just the opposite direction. So the difference between the two is the same. It's 1.19 units, whatever units they're in. But the p-value is different. In this case, when we didn't do an adjustment, the p-value was 0.4. When we did, it was 0.68. In other words, when we make an adjustment, it is going to push the p-values up so that we are less likely to reject the null, and thereby it saves us from being as wrong in saying there is a difference. Again, we'll talk about that more later on. When it comes to the effect size, we're going to call that eta squared. With the p, it's sometimes called partial eta squared. What it's telling us is the amount of movement between the groups. How big is that compared to the amount of movement between the groups plus the amount of movements within the groups, or in other words, all of the movement? Another way of saying that is how much of the variability is accounted for by the groups versus everything else. So you can see it again here. Again, eta is called, it's spelled this way, looks like this. It's just telling us how much of the variability in our data is due to the groupings versus everything else that we see. Like with Cohen's d, there's going to be some rough cutoffs that we can use. So 0.01, 0.06, and 0.14 go with small, moderate, and large, respectively. And then lastly, interpreting the results. We're going to interpret it just like we've done before. In this case, there is an example around page 382 that you can consider using as a template. We'll give some examples in class again, like we've done. When it comes to ANOVA, there's one way and two way. The example we walked through really briefly looked a lot more like one way. We were just talking about a single variable with 3 different levels, but we might have 2. When you're considering these, a one-way ANOVA has just one predictor. and a test for any differences across the groups on that one predictor. When it comes to a two-way, the two-way ANOVA has two predictors, and it tests for any differences across the groups for both predictors and their combinations. What's called an interaction. That's the interaction of the two predictors, which tells us, does the effect of one depend on what group you're in and the other? Consider this example. So interaction is when the effect of a predictor depends on the other. This one, we're comparing males and females, GPA, with whether they didn't have a tutor, a group tutor, or a private tutor. So our question might be, depend on your sex, your male or female, are you better off having a tutor, no tutor, or a group tutor? And what we're seeing is for females, they do not do very well on average with no tutor. They do pretty well with a group tutor, but with a private tutor, they do awesome. For males, they do better than females with no tutor, but that's not fantastic. Group tutor, they do a little bit better. But a private tutor, they really don't do much better than the group tutor. This gives us some results really quick. We can say, well, the effect of the tutoring, whether you're a no tutor, group tutor, or private tutor group, the effect of that depends on whether you're male or female. If you're female, then being in the private tutor group is the best. If you're male, then the group tutor and private tutor are basically the same, so you could pick either one. When it comes to interactions in two-way ANOVAs, we are starting to get really complicated stuff. Because of that, I really believe that our example in class with Jamovi is going to help illustrate what this means. As you're thinking about this before class and as you raise questions on the discussion board, be thinking about possible interactions that you've seen in real life. That the effect of one thing depends on what you are in another. One final one I want to share interaction-wise is looking at the effect of type of food on enjoyment depending on the topping that you choose. And I'll show this in class, but consider both ice cream is one of the groups that we create and hot dogs are another group. So we bring people in and we say, okay, we're going to give you either ice cream or a hot dog. Half the people we give ice cream to, half the people we give hot dogs to. But we also have another variable that we're randomly assigning, and that is the topping. And for half of the groups, or half of the people in the ice cream group, we give fudge, and the other half mustard. And for the hot dog group, we give half of them fudge and half of them mustard. And if you can think about what the enjoyment would be like for each of those, ice cream would be very enjoyable when you have fudge, way less enjoyable when you have mustard. But it would be the exact opposite for a hot dog. So what we'd be able to say is the effect of the type of food, either ice cream or hot dog, on enjoyment of the food depends on the type of topping you have. You're really going to enjoy the ice cream if it's fudge. You're really not going to enjoy it if it's mustard. Those are interactions, when the effect of one thing on the outcome depends on the other variable. We're going to show a few of these in class, see if we can find some with some of the data that we have. But be thinking about possible situations where you've seen it. This is a short discussion on ANOVA. I'd like to do this one a little bit more in person. Please, as you're reading and watching this lecture, post any questions to the discussion board, and that'll give me some time to think about what your questions are and where there's some holes, and we'll make sure we discuss it in class.